Hello.
Good evening, sir.
Yeah. Can hear me, right?
Yes, sir.
Okay. What have you done in the last few days?
Sir, I completed chapter 4 and 5 of HCV, the exercises and like the reading, like everything.
Okay. You have any doubts?
Yes, sir. Few notes. And
Tell me which ones.
sir, um,
Chapter 4 and 5 or 5 and 6?
sir, 4 and 5.
Friction chapter is not yet done.
Sir, sir, no.
Okay.
Sir, firstly, chapter 4,
Hmm.
objective part 2.
Okay.
Question 7.
Action and reaction
Yeah.
act on two different objects. That is correct.
Mm.
What is the doubt here?
So, do they have resultant 0 because they're acting on two different objects?
If you think of them as force vectors, then obviously the resultant of the two vectors is 0.
Yes, sir.
You will not apply and make it on one object, but technically the resultant of the two vectors will be 0. Right?
Yes, sir.
Although they are acting on different objects. So you will not count them in one free body diagram. But technically it is correct that the resultant of the two will be 0. Right?
Yes, sir.
What else?
So, chapter 5. Uh, The question 19 of exercises.
Saying the force of buoyancy exerted by the atmosphere on a balloon is B in the upward direction and remains constant. The force of air resistance on the balloon acts opposite to the direction of the velocity and is proportional to the velocity. So there is a balloon. Force of buoyancy is always acting upwards, B, and is constant. And force of air resistance, let's call it Fr, is going to be opposite to the velocity and is also proportional to the velocity. Right? Now, initially, what they had said was the balloon carries a mass m and is found to fall down towards the Earth's surface. Balloon had mass m and is falling down towards the Earth's surface with a constant velocity of v. You have to unmute yourself. Don't keep yourself on mute.
Yes, sir.
So it is going down towards the Earth with a constant velocity v. Which direction do you think air resistance is acting right?
Sir, in the upward direction.
So upward air resistance will act and the magnitude will be proportional to v, right?
Yes.
And mg will be acting downwards and b is acting upwards. This is the situation. And they said that it is going with a constant velocity. So if it is constant velocity, obviously acceleration is 0.
Yes, sir.
Right? That means if acceleration is 0, that means all the forces are balanced. So the equation of motion for it is b plus fr minus mg is equal to 0. Right?
Yes.
Now in the second situation, some mass has been thrown off from the balloon. Mass has been removed from the balloon. Now the balloon is rising up with the same velocity v. right?
Yes.
So the new mass of the balloon, let's say, is small m. The forces are small mg downward. Buoyancy force is still upward, but this time air resistance will be which direction?
So downward.
Downward Fr, and it is still proportional to the velocity, so magnitude of air resistance is same as before, right?
Yes.
Because they are saying the same velocity v's.
Yes.
Now it is rising with a constant velocity. It is going up with constant velocity, that means acceleration is again 0, but this time the equation will be b minus small mg minus Fr is equal to 0,
Yes,
right?
sir.
So looking at these two equations, we have to find the amount of mass that was removed. So you have to find basically m minus smaller.
Yes, sir.
So first of all, what you can do is simply add the two equations that will cancel the Fr, right?
Hmm.
We'll get 2b minus m plus m g is equal to 0.
Hmm.
And basically that is equal to 2b by g is equal to m plus m here.
Hmm.
And we have to find m minus m, right?
Hmm.
So in order to find m minus m, I will have to subtract, or basically I will say b plus Fr is equal to capital Mg and b minus Fr is equal to small mg from the two equations.
Hmm.
So if I subtract, I will get 2Fr is equal to m minus m into g, right?
Yes.
So m minus m is coming out to be 2Fr by g, right?
Yes.
And now I need this, but Fr I don't know. Fr is actually what? Mg minus b.
Yes.
So you can say 2 by g into this Fr.
Yes.
2 by g into mg minus b should be your m minus m. So it is basically 2m minus 2b by g.
Hmm.
Now the answer is in terms of things that have been mentioned in the question. The question, it was mentioned the b and the m and the g and all. You are getting m minus m value. You are just not writing it in terms of Fr. You are writing it in terms of mg minus b.
Hmm.
From the two equations only we have gotten everything. Thing weird has happened.
Hmm.
Do you understand what is happening?
Yes, sir.
Okay. What is the next one?
Sir, 23.
Right. So you have to look at the Atwood machine and of the previous problem, and the larger mass is stopped for a moment. Okay, so previous problems Atwood machine, if you look at, this was the situation M1 and M2. M1 was 300 grams and M2 was 600 grams, right?
Hmm.
System was released from rest in the previous problem, and okay, so let's say system is released from rest. Obviously it will go down and this will go up,
Yes.
right? So what you have to think about is 2 seconds after it was released, after system is set into motion. System is set into motion.
Hmm.
So it is easy in this problem to find the acceleration of the whole masses. You can say it is m2 minus m1 by m1 plus m2 into g, right? So
Yes.
the acceleration will come out to be 300 by 900, so g by 3, right?
Hmm.
This is going down with g by 3 and this is going up with g by 3. And at the end of 2 seconds, what will happen is this will rise some distance, right? and this will fall down some distance. And at that moment, both the blocks will have some velocity. Velocity would be q plus at, so g by 3 into 2 and g by 3 into 2, right?
Yes.
But at this moment you stop this block. You catch it and you hold it, right?
Yes, sir.
So if you hold it right now, the motion, you have cancelled this velocity and converted it to 0 for a moment, right?
Yes.
But what will happen to this? This will not stop, right?
Yes.
However, after you have stopped this, the string becomes loose, right? Because as soon as this goes a little ahead, now the string has gone up, but this side the string is not falling, right?
Yes.
So the string has become loose as soon as you stop this. So no tension will act after that, right?
Yes.
Do you understand what I'm saying?
Yes, sir.
No tension will act, and what will happen is this will rise. So the forces on it are now going to be basically just gravity, right?
Yes, sir.
2g by 3 is the velocity of this block upward, but force is only mg.
Yes.
Mg force, so acceleration is downward g, right?
Yes.
So basically what will happen is it will rise up to a certain extent, then slow down to 0 and then start falling back down.
Yes.
Once it starts falling back down, you will realize that once it reaches back to its position here, at that moment, after that, when it tries to go down, string becomes tight again.
Yes, sir.
Do you understand what I'm saying?
Yes.
It goes up a little bit, stops, comes back, falls down, and then wants to go down. Then the string becomes tight again, and then the tension comes again, right? So this is the time that elapsed that you have to find out. Do you understand?
Yes.
That is easy to find. You can just, yeah, you can just calculate that, right? What is the next one?
Sir, 31.
Okay. So 31 and these types of problems are about constraints. If you are unable to solve this, then are you sure you have understood the constraint part or not?
Yes, sir. I managed to solve it. I got the answer, but like I wasn't really sure.
Okay. So this is the situation. Okay. Everything is frictionless and all, and the system is released. And now you have to find out acceleration, tension, and everything. So you have to realize that there are two strings in this problem. There is this string which goes around and connects like this, and there is this string, right?
Yes.
So now what you have to think about here is the pulley here is movable. Pulley B is movable, and if it is a movable pulley, you have to understand that the connection of 2m to the pulley is to the center of the pulley, right? So if the pulley moves ahead by x, obviously 2m also must move ahead by x, right?
Yes.
Because otherwise the length of this string will change, right?
Yes.
We are assuming that strings are inextensible. Strings are inextensible. The length of the string cannot change.
Yes.
So if you assume that, you will realize that whatever is the velocity of pulley B is the same velocity of this 2m, right?
Yes.
And therefore the acceleration of pulley B is the same as the acceleration of 2m.
Yes.
Okay, so that's fine. We have to find out acceleration of 2m. We also have to find out acceleration of m, right?
Yes.
So right now we don't know whether there is a connection between the acceleration of 2m and the acceleration of m. right?
Mm.
These are two unknown variables for us, but there will be a connection, which is what we have to figure out. Okay.
Yes.
Why do we have to figure out this connection? Because without knowing the connection between these two variables, you will not have enough equations to solve both the things.
Mm.
Do you understand what I'm saying?
Yes, sir.
If you do equation for this body, let's say tension here is T, you will say mg minus T is equal to m times A of m, right?
Yes.
And if the tension here is T, the tension in this whole string is T till here. So the pulley will experience a force of T this side, T this side. And therefore the force on this should be 2T,
Yes.
right? The tension in the second string must be 2T. Why does the force on the pulley have to be balanced?
So because the pulley is massless, so it
Because
cannot.
it is massless, you cannot have net force on it because that will produce an infinite acceleration, right? Force is equal to mass times acceleration. If m is 0, F by m will become infinite, right?
Yes.
You have to have force also must be 0, then only it works out that it is massless, right?
Yes, sir.
Because acceleration cannot be infinite, right?
Mm.
So since forces have to be balanced, we know the tension in the second string, this string is 2T. So the equation for 2m mass is 2T is equal to 2m times A of 2m, right?
Yes, sir.
So you can see these two equations, there are three unknowns, tension, AM and A2m, right?
Yes,
You
sir.
cannot solve two equations with three unknowns. So we need another equation, which is basically called the constraint relation, which is basically a connection between the acceleration of mass m and the acceleration of mass 2m.
Mm.
Because in this situation, you can see that it's not like both the bodies are completely free of each other, right? They are connected to each other with some pulley system. So there will be some link between their accelerations, right?
Okay.
And that is what we have to figure out here, how to find the connection between their accelerations. So the idea here is to always take advantage of the fact that the strings are inextensible,
Mm.
right? So if the strings are inextensible, you have to think about it and realize that let's say this goes down by a distance y, right?
Yes.
So what will happen now? Look at the string here. The string here is longer and this distance, extra distance is y, right?
Yes.
Obviously, because of that, the pulley has gone ahead. And let's say it went ahead by x distance, right?
Mm.
So let's say the new pulley was somewhere here, and this was the situation now. And the new depth is more by y, right?
Mm.
From this point, the pulley has moved ahead by x, right?
Yes.
So now you can say that look at the string, this string, which was rolled around the pulley and went down on this side, right hand side, right?
Yes,
If you
sir.
think of that string has lost a length of x here and a length of x here, right?
Yes, sir.
In the top portion, there is a decrease in length by minus 2x, right?
Mm.
And in the bottom portion, on the right side portion, there is an increase of plus y.
Yes, sir.
So minus 2x plus y should add up to 0, right? Total change in length.
Yes, sir.
So the total change in length of the string cannot happen. This is the increase in length. This is the decrease in length of the pulley, right?
Yes.
Not of the pulley, of the string.
Mm.
Since the total string cannot change its length, you have y minus 2x equals 0. And if y is equal to 2x, that means the displacement of this mass is connected to the displacement of this pulley, right?
Yes, sir.
When this mass moves by y, the pulley moves by x is equal to y by 2,
Yes.
right? So pulley moves only half the distance that this mass falls, right?
Yes, sir.
If you differentiate this relation once, you will get a connection between the velocity of this mass and the velocity of the pulley. And if you differentiate that once more, you'll get a connection between the acceleration of this mass and the acceleration of the pulley,
Yes,
right?
sir.
So if the acceleration of this mass is am, the acceleration of the pulley must be am by 2.
Yes, sir.
And we have earlier seen that whatever is the acceleration of the pulley is the same as the acceleration of the 2m.
Yes, sir.
Why? Because they are connected by a straight line type of a string, right? There is no twists and anything.
Yes, sir.
So therefore we get the relation a to m is equal to am by 2, right?
Yes.
And once we have this relation, the equations are now very easy to solve. You can just say that this becomes 2m into a to m, you can write am by 2. So this becomes mam. And basically you're getting 2t is equal to mam and mg minus t is also mam. So you're getting mg minus t is equal to 2t. So 3t is equal to mg, t is equal to mg by 3, right?
Yes, sir.
And if t is mg by 3, you get 2mg by 3 is equal to mam. So acceleration of this is coming, am is coming out to be 2g by 3, and therefore a to m would be g by 3, right?
Yes, sir.
So all the things you can solve now. In your FitG or in your coaching and all, they might not have done the strings thing. They might do things like t into x tension and all.
Yes, sir.
I don't know how they explain it in your class, but
Sir, they did what?
okay. What did they say about the tensions and all?
So they said that so there can be no net energy absorbed or gained by the strings. So whatever is it. So if the strings are doing some work in moving something by x, then that same work must be used up in some other part.
So that method is sometimes useful. The method is saying that total work done by tension will be 0.
Yes,
Done
sir.
by tension in the whole system will be 0. Basically, they will say the tension here is T. So, and the body goes down by, let's say, X. So work done by tension is minus Tx here. And here the tension is T and tension is T. And work done by tension here would be basically 2T into Y, right?
Yes, sir.
Because this has gone ahead by Y. So they will say 2T into Y is equal to T into X, or 2T into Y minus T into X is 0. Total work done by this string's tensions is adding up to 0, right?
Yes, sir.
It comes out to be the same thing, but the problem with that method is that you don't know any reason why this has to be 0. Right now you don't know any reason for why it should be 0.
So
This is
this
just,
string cannot absorb energy
but
because the
why?
uh,
There is no reason why it can't absorb energy. Why can't? What do you mean absorb energy? String can do work by tension. You're not saying it can also absorb energy. Like suppose this was, why is it not equal to 0? Maybe the string does some work. String doesn't have to absorb energy to do work. It is doing work on the other part of the system, right?
yes, sir. So some work is also done on the string.
Let it be done.
So then that would make that equation not equal to 0.
No, what I'm saying is, let's say this tension does some work on this mass. That work is minus Tx. This
Yes.
tension T and T does some work on this pulley. That was 2Ty.
Yes.
Right now, you don't know any reason why it has to add up to 0.
Hmm.
This is just a statement that has been given. You don't know any reason because you have not done properly work per energy chapter only.
Yes, sir.
So I would recommend that you don't use this explanation, because the explanation is not making any physical sense right now. Why should total work add up to 0? There is no reason. In many situations in the future chapters, you will see that total work doesn't have to add up to 0. That's the main point of the chapter on work energy, where if total work is non-zero, then there is a change in kinetic energy, right? So that's why I don't prefer this explanation. It will help you solve some problems, but the better explanation is the fact that we are assuming the strings are inextensible. That's why in HCV also it is only by string length. They have not used any work and all.
Yes, I did not.
If you see the example, they keep track of the length of the string, point A, B, they measure the length of the string, and if you move some distance, then A goes to A dash, B goes to B dash, and you keep track of the total length of the string.
Yes, sir.
If you keep track of it properly, then you will get the connection between the displacements.
Yes, sir.
If I hope you have seen the example in the HCV book also.
Yes, sir.
That's how you should usually explain things. That's how you need to understand it. If strings were extensible, then they are not strings, they are behaving like springs.
Yes, sir.
Right now, we are not dealing with such situations. Okay. So that's how you think about it. What else, tell me?
So 39.
Okay. There is a man, 60 kg weight, standing on a light weighing machine that is kept in a box. Okay. There is a weighing machine here. Man is standing on it. Man is holding, there's a pulley like this. Man is holding one end of the string. And the
Yes.
pulley is connected to the lift also. And man's weight is 60 kg. The whole lift's weight is 30 kg. The rope is hanging like this, okay. If the man manages to keep the box at rest, what is the weight shown by the machine? The first thing you have to realize is, how does a weighing machine work? So if a man is standing on a weighing machine, the weighing machine actually reacts to the normal force, right?
Yes, sir.
Because free body diagram of the man shows mg, but this mg is not acting on the weighing machine. You have to be clear on that. Do you understand?
Yes, sir.
There are two forces on the man, normal force and mg. Both of them are acting on the man. But where did this normal force come from? It was coming from the weighing machine, right?
Yes.
Because he is standing on the weighing machine,
Yes.
right? So since the weighing machine exerted a force upward normal, the man exerts by Newton's third law downward normal, right?
Yes.
This is the force that actually acts on the weighing machine.
So
This is
suppose
the,
we push the weighing machine up by some force. Like,
suppose you,
sir, in this scenario, won't the force, like, he's pulling it with the force, with some force, so that force, the tension force is pulling the man up. But then also the tension force is pulling the weighing machine up, right?
no, tension force, how is it acting
Tension
on weighing
force is
machine?
pulling the box up and therefore pulling the weighing machine up.
Weighing machine is not part of the box. I mean, it is inside the box, but it's not, tension is not acting on the weighing machine.
But the normal force from the box is pushing the weighing machine up.
A normal force on the box, that's fine.
So then will that like change his weight or something?
You have to, you have to take into account what force weighing machine registers. The only force that changes the reading of the weighing machine is this normal.
So the
Whatever changes this normal will change the weighing machine reading.
so not the bottom normal.
So the bottom normal also acts on the weighing machine, but do you think that will show up on the reading on the scale?
No.
Then if you keep the weighing machine on the ground, it should automatically show the normal force of the ground.
That it doesn't, but if you increase the normal force of the ground.
नहीं, तुमने weighing machine देखा है कभी?
Yes.
Have you stood on a weighing machine?
Yes.
So when you don't stand on it, does it show a reading?
No.
So normal force is not acting at that moment.
So it is acting, but will it be subtracting that some fixed value?
No. Is the normal force, this is a weighing machine, is the
Yes.
normal force from the ground showing up in the reading?
No.
So should you consider it?
No.
That's it. What is showing up in the instrument is what force acts from top on it. That's
Okay.
how the instrument is designed.
Hmm.
You will not be detecting forces from the ground on it.
Hmm.
If it was detecting it, then the weighing machine should automatically show its own weight then, right?
Said is it like showing its own weight in this reading minus its own weight? No, right?
No.
Hmm.
You have to understand how the machine works. The machine is basically a simple spring inside, dude.
Yes.
If you stand on it, it is compressed and it shows a reading.
Hmm.
The spring is not already compressed.
Yes, sir.
It is not reacting to the normal force from the ground.
Hmm.
Do you understand what I'm saying?
Yes, sir.
It will only react to vertical forces coming from above. That's how the machine is made.
Yes, sir.
So in this question, we are going to concern ourselves with what is the normal force that the man exerts on the weighing machine to see the reading on it.
Hmm.
So now if you draw the free body diagram of the man, there is upward force of tension, there is normal force from weighing machine on the man, there is mg 600, right?
Yes.
Okay, so since everything is at rest, you can say that n plus t is 600, right?
Yes.
Initially he was hanging in such a way that everything was in equilibrium, right?
Yes.
So n plus t is 600 is coming. Our job is to find n. That shows the reading. Correct?
Yes, sir.
Now if you take the whole thing as a system, whole thing, everything inside, right? You will realize man plus weighing machine plus everything, right? Total weight is 90, so 900 is down, right?
Yes.
And what is the upward forces? 2t.
Yes, sir.
This is a t acting here, this is a t acting here, right?
Hmm.
So obviously 2t must be equal to 900 if equilibrium is happening.
Yes.
Do you understand what I'm saying?
Yes, sir.
So t is 450, and if t is 450, n is 150 then, right?
Hmm.
N is 150 means right now 15 kg it is showing. The weighing machine is showing 15 kg weight right now.
Hmm.
In the new situation, what he wants is to see his actual weight, right?
Hmm.
In the second situation, everything is a little different because he wants to see his accurate weight, right?
Yes.
So he has to now pull with a force such a way that he accelerates the whole system, right?
Yes.
So we will say the situation is such that the situation is such that if he pulls hard enough, the acceleration will be upward for the whole system, right?
Yes.
So let's say acceleration is this. The equations will be now n plus t minus 600 is equal to 60a for the man, right?
Hmm.
And if you take the whole system also together, you will say 2t minus 900 is equal to 98, right?
Yes.
Are you understanding what I'm saying?
Yes, sir.
Now, in this situation, he wants his real weight. So we know the normal force, what should be shown.
Mm.
Why? Because he wants to see accurate weight. No, so normal force must be 600 then.
Yes.
So you will say T is equal to 60A then, right?
Yes.
And you will get basically 60A minus 900 is equal to 90A.
So
Something has gone wrong.
sir, 120A minus 900.
Oh, that was what was wrong. 120A minus 9. So 30A is 900. So you have A is 30, right?
Yes.
You have to accelerate upward at 3g, 3 times the acceleration of gravity. And that time the force of tension would have been how much? 180 g, so 1800 newton.
Mm. Yes, sir.
He has to put an upward force of 18 or pull the rope with 1800 newton. Only then will he see his actual weight.
Yes, sir.
Do you understand what is happening?
Yes, sir.
What else?
So that's it.
Okay, you have to do friction chapter, circular motion chapter also as fast as possible, because in Fiji they are doing now work by energy.
So they're still like they're basically like doing assignments for Newton's laws. So after that they'll start work hard.
Okay, that's fine then. But your job is to do these chapters. Okay.
Yes, sir.
Uh, Try to finish as much as possible in friction and circular motion. If you need more classes, let me know whenever you are done with anything. And if you have doubts in trigonometry, also you have to do chapter 8 and chapter 9. So, are you starting that? Are you doing it?
Yes, sir.
They're doing circles now in Fiji.
Yes, sir. They just started circles.
So, in the next class, when we do maths, what I want you to do is bring all the doubts of straight lines and chapter 8 and chapter 9 in trigonometry.
Yes, sir.
Anything that is pending in straight lines and anything that is a doubt in chapter 8 and chapter 9, all of those things have to be discussed.
Yes, sir.
Let's do next class for maths, because it will take you a few days to do physics chapter 5 and chapter 6. So next class will be maths, and we'll do the 3 chapters, chapter 8, chapter 9 and straight lines.
Mm.
Okay,
Yes, sir.
fine. We can do the class on Sunday if you're free. Otherwise, we'll do it coming.
Sir, is Monday all right?
Yeah, Monday should be fine.
Yes, sir.
Okay, that's all for now. I'll see you next class then.
Thank you,
Get
sir.
all your doubts.
Yes, sir. Thank you, sir.